Okay, guys, so today we're here to talk about lines, rays, line segments, and what we could do with those and why they're all a little bit different, but they are very similar. So after today, you should be able to find the distance between points on a number line and find the distance between points in a coordinate plane. We're not going to really look at the coordinate plane stuff too much, just because we're not going to be working with the distance formula just yet, so don't even worry about that. We're just going to be looking at what line segments do and why they're different from just a regular line. So first, let's go ahead and talk about a line again, which we talked about yesterday. So a line is continuous between any 2 points, could be more than two, and this is a collection of points. Remember that. Like I just said, it could be more than just 2 points. It's a collection of them because we could draw an infinite amount of them on the line. But let's pretend we had 2 points on this line, A and B. So just to review, we would name this line AB like this. You could say line AB. But again, remember, it's continuous in both directions. So up here it asks, can you measure a line? Like I just said, you cannot measure this because it is infinite in both directions. So there's no ending. There's nothing that can measure that. So the answer would be no to that. Now, a ray. What is a ray? Again, a ray is a line with only one endpoint. But as you can see up here, we still have that arrow here, so it is continuous in one direction. So now, let's talking about naming the ray here. So let's pretend that this is point C. Now, let's put a random point here. Let's say it's point D. So now, how would we name this ray? So this ray, we would again name with points, but it's just a little different of a notation. So instead of drawing the 2 arrows on top, this would be ray CD. Okay? So now the question for this one, again, is can you measure a ray? So just like before, we have one end where it is infinite in one direction. It goes on forever. But there is a hard stop here. We still cannot measure it, though. There is one direction where it goes on forever, which does not allow us to measure it. Now, let's look here. The difference with a line segment is now we see 2 hard stopping endpoints. Can we draw points in between? Yes, but we see a definite end to this. So let's give these names first. So we have points E and F. So to define it, a line segment has 2 endpoints and can be measured. So therefore, there is a size to this. If we held a ruler up to it, we can get a definitive answer. So yes, we can measure a line segment. So look at the differences. Here, we have a regular line, continuous in both directions. A ray is considered continuous in one direction, and then a line segment has 2 hard stopping endpoints. So now let's move on. So why would we need to do this? So just like how you measure a piece of wood, you can measure a line segment and a segment, like we just said before, is a part of a line. And what does it have? 2 endpoints. Okay, so picture a piece of wood. It is technically a line, but it has definite ends to it. So how can we measure this? You might see something like this here below where it's on a number line like this, and you can count the number of spaces that's in between the endpoints. So let's look at this, for example. We're not going to use a ruler for this one just yet. We do have numbers on here. So let's look at the distance between line segment A and O. So if we look at A and O, so that would be the line segment that goes from A to O, we have a definite measurement. So this is about 0.5 here. And then if we go up, we have 1, 2, 3, 4, 5. So our measurement here would be 5.5. So all we're doing here, once again, is we're just counting the spaces between the numbers, or the endpoints, sorry. So let's look at now TO. So TO, here's our endpoints, segment TO. We would go ahead and look and count. So from T to O, we have 1, 2, 3, 4, 5, and 6. So that would be 6. Now, I think you get the hang of this. All we're doing is counting the space between the points. So between O and S now, if we use a different color, we have 1, 2, 3. And so on and so forth. Now, if we just kind of breeze through these, I think that this concept is something that should be a little bit more comfortable and easing. Seeing the number line, we should be able to count these boxes. So again, A was here, just about in between. So from A to C, that would be a 0.5, and then 1. So 1, from -3 to -2 is 1, and then we have our 0.5 here. The distance would be 1.5. Now let's look at T to S. T to S, 1, 2, 3, 4, 5, 6, 7, 8, 9. S to T, that would be the same exact thing. We're just going in the other direction. We're just saying one endpoint first. So we did T to S. S to T is still the same distance. Now, take a look. You might say, but we're going in reverse on the number line. We are going backwards this way, but there's a reason for these. They are the same no matter which endpoint goes first. And that reason is because distance is always positive. So anytime you're measuring distance, no matter what it is, it's never negative. So the easiest way to think about this would be driving a car. So if you drive a car from your house to school, you wouldn't say you were going -2 miles. Or if you went from your house to school and then the school to back, you wouldn't say you drove -2 miles back to your house. You would have driven 2 miles. So drive a car, think about that example. It's always positive distance. Okay. Let's look at some word problems. So take a look. The other day, my friend Doug got on a train to New York City. So that was his final destination. We'll call that an endpoint. So let's just put a dot here or a point. We'll call that New York City. So he got on at the Ronkonkoma train station. So picture getting on the Ronkonkoma train station and driving the train or riding the train to New York City. Now, after the train had traveled 5 miles, it stopped at the Farmingdale station. So we're starting at Ronkonkoma. Say we go 5 miles. Now we hit Farmingdale. So that's 5 miles total from Ronkonkoma to Farmingdale. Now, it says, in total, Doug rode the train for 32 miles. So that means from Ronkonkoma all the way to New York City is 32 miles. Now, I don't know if this is true, but seems like a pretty good estimate. So we traveled a total of 32, but from Ronkonkoma to Farmingdale was 5. So now it asks, how many miles did Jordan ride the train? Jordan got picked up here. Jordan was picked up in Farmingdale. So we're really looking for this missing distance here. So how would we solve that? We would set up a simple algebraic equation. So what do we need to do? So if the total is equal to 32, we'd have to add these two line segments. So we have our segment here of 5, and then we have our missing segment here of x. So if we do that and set up our equation, all we do is subtract 5 from both sides, and we get that the distance from Farmingdale to New York City was 27 miles. Pretty straightforward when you draw yourself a diagram. So always draw pictures of a line segment when you can. It will help you visualize what's going on. So let's move on. So now let's talk about something a little different called segment addition. So we have this point Q between our two endpoints, P and R. So we basically have two line segments added together. So we have our segment PQ here, and then our segment QR. So now what it's saying is finish this equation here, or this simple addition. So PQ plus QR, if I add this line segment and this line segment, we get the whole line segment, which is P to R. So technically all we do is add two line segments, and then we combine them with the two big endpoints. So then similarly, if we did PQ plus QR, then Q is between P and R. That's all it is saying if you add two line segments together, now we have two different endpoints. So we use the most left and the most right endpoint to rename the line. So pretty simple as far as that goes. Now let's move on down here. So now we're just going to use kind of a ruler just for basic measurements. So if I pull up a ruler here and I put this along this line segment we're about to have. So sorry if it's not perfect. So let's say I draw my line from A to B to C. Okay? So if we were to count this up, this ruler is in centimeters. Let's move it over nicely. So if we take the ruler and we move it over and we line up the points and measure it, again, this is in centimeters. So we have 1, 2, 3, 4, 5, 6, 7, 7.5. So let's say this segment is 7.5. From here to C is 0.5. We have our 1, 2, 3. So we have 3.5 and 7.5. Okay, so now let's take our ruler away. So this line segment is about 7.5 centimeters. And this line segment is about 3.5 centimeters. Now let's read our question. So it says the points A, B, and C are shown below. And then it says find the values of AB, BC, and AC. So we got our segment AB here, 7.5 centimeters. We also got our segment BC, 3.5 centimeters. So now, just like I said before with our segment addition, if we wanted to get AC, we would have to do AB plus BC. So we're just adding the lengths of our two segments. So we had 7.5 plus 3.5, and that will give us 11 centimeters. So all we did was we did our segment addition we just showed above, and we measured our two segments put together. So then it says, what is true about the value of AB plus BC? What does this tell you about these 3 points? So you got to think about what we talked about the day before. So we showed that these points are all in a straight line by showing that this plus this equals the total distance of this line. So there's a special word that we talked about. So that means that points A, B, and C are collinear. If we can show that AB plus BC equals the whole line segment when we measure, that proves that they're collinear. So once again, we have to show this to prove the collinearity. So if we move on, we can do the same kind of thing here. So once again, let's take out our ruler. So if I put my ruler along these points here, let's go ahead and draw ourselves a straight line. So again, if I count in centimeters, let's line up this ruler. Oops. Line it up to measure. So let's just give about answers. So from A to B, we have a measurement of, let's say, 1, 2, 3, 4, 5, 6, 7, 8. 8 centimeters. Then from B to C, we have 1, 2, 3, 4. Let's say that's about 4.3 centimeters. Now, if we look at the measurement to get the whole entire line or the combined line segment, all we have to do is add them. So to show collinear, all we have to show is that 8 plus 4.3 equals 12.3 centimeters, which is the measurement for the whole line segment. So we just proved that again by segment addition. So now let's look at these points here. The points P, Q, and R, also S, are collinear. So we're told that this is a straight line. So it says find the lengths of segments PQ and RS to the nearest millimeter. So let's first do that. So if I take out my ruler, we can get our measurements. So we're looking for PQ and RS. So 1, 2, 3, 3.5. About 3.5 centimeters. RS, 1, 2, 3, 3.5. 3.5 centimeters for both of those. Now, what can you say about the lengths of PR and QS? So let's move this out of the way. So we're looking for PR and QS now. So PR, so this segment, and then we're also looking for this segment. So what can we say now? We have two congruent line segments here. So we have this one, PQ, and also RS. Now, if we add on the piece QR to both of them, and we're looking at PR, and then also looking at QS in the yellow, if we're adding on the same piece to equal segments, then we're already good to say that they're congruent. It does not matter which we add on. We're adding on the same piece to congruent segments. So yes, they are equal. So PR and QS are the same length. So from here to here and here to here. And once again, that's because we measured this, and then we added on the same segment to both and showed that they were equal. So we don't even have to go ahead and measure. So now if we move on, we have some practice problems here. So let's do one together, and then you guys can pause the video and take a practice on your own. So it says, in the diagram below, points A, B, and C are collinear. So we're already told that. So let's go ahead and draw a nice straight line with our ruler. So if I take my ruler here, and match it up, now I'm going to go ahead and I'm going to draw a straight line. Okay, so they're told that they're collinear. Remember, keep that in mind. And it says, answer the following questions based off of the diagram. So again, it's not drawn to scale. So what that means is that it might be a little bit different appearing depending on the size of your screen. So let's look at the first question. So what I'm going to do is I'm going to model with the diagram up here to show how we can do this by using the picture. So it says AC is equal to 5. So we're doing A. So A to C is equal to 5 inches. C to B is equal to 3 inches. What is the length of AB? So what's now the length of the entire segment? So all we're doing here is our segment addition. So we do AC plus CB, and that should give us our AB. So we'll do our 5 plus 3, and we get 8 inches. So now what I want you to do is I want you to pause the video, and I want you to practice B, C, and D using the diagram. You could draw yourself a little sketch in here like this to resemble the picture to help yourselves out. I recommend doing that so you're not putting a bunch of numbers on one line. So let's pick up here now. So B, similar type of problem, we're just given different measurements. So it says from A to C, it's 6 1/4 inches, and then C to B, it's 3 1/2. Find AB. So we're doing the same exact thing we did as the last problem. All we're doing is adding the two segments. So 6 1/4 plus 3 1/2. And if you do your fraction math, you will have a calculator. You get 9 3/4 inches. So that's the total line segment AB if we add the two. Now C, a little different, but nothing too crazy. We're still using the same principles here. So A to B, meaning the measurement of the entire number line, is 10.2 centimeters. C to B is 3.7 centimeters, or B to C. So how would I get the measurement for A to C? I would have to subtract 3.7 from the total. So 10.2 minus 3.7, that would give you 6.5 centimeters. So all I did was subtract the part from the whole. Now the last one, a little more challenging with the numbers, but same concept here. The total length is 4 3/4 of an inch. We subtract A to C, 3 1/4, to get B to C, this length here. So when I do that, again, use your calculator, we get 1.5 inches. Okay, so pretty simple. We're taking parts from the whole and subtracting, or we're adding two segments together. So now we might have to draw our own pictures here and give ourselves an idea. So you might be faced with a word problem where you're not given a segment, you have to draw it yourself. So if we have PR equals 22, so P to R, so we have some line segment like this, is 22. And then from Q to R, so some point in between, obviously, because it's smaller than 24, is 7. Now we're looking for P to Q. So how would we do that? We'd have to take 22 and subtract 7 from it to get this missing piece here. So 22 minus 7 equals our missing piece, X. When we do that, we get that PQ is equal to 15. Pretty simple there. So it's all about drawing the picture here to help yourself out. So then for the next one, same thing. Same kind of diagram. We have PQ equal, oops, sorry there. Q is our midpoint, or our middle point. So if we put our Q in between, and we have our R at the end again, we have something like this. So from P to Q is 3x plus 2. Q to R is 18. And we're given our total distance with a variable, which is 5x. So how would we do this now? How would we solve? Well, we have this segment plus this segment equals 5x. So we have 3x plus 2 plus 18 equals 5x. So same thing with segment addition. We're adding P to Q and Q to R to get us P to R. So when we do that, we have some algebra to do here. We have 3x plus 20 is equal to 5x. I subtract my 3x. I have 20 equals 2x, and I get x equals 10. So now it asks us to find PQ here. So let's take our x and plug it back in. So if I plug it back in, I do 3 times 10 plus 2, which is equal to 32. So my missing segment was 32. I had this piece here was 18. So if I add those together, my entire segment had a measurement of 50. Now for our last one here, same diagram. PQR. P to Q has a measurement of 2x. Q to R has a measurement of 2x minus 4. And the entire segment has a measurement from P to R of 26 minus x. So now we once again do the same thing. We add the two segments to get our entire segment. So we have 2x plus 2x minus 4 equals 26 minus x. So a little bit trickier algebra, but nothing too crazy. Let's go ahead and solve. So now if I do this here, I'm going to combine like terms. I get 4x minus 4 equals 26 minus x. I'm going to go ahead and I'm going to get my x on one side. And when I do that, I'm going to add x. I get 5x. I add my 4. I get 5x equals 30. And I go ahead and divide, and I get x is equal to 6. So now x equals 6, but I still have to plug it back in. So if PQ was equal to 2x, QR was equal to 2x minus 4, and PR was equal to 26 minus x, if I plug that 6 into everything, I should get it. So go ahead and make some room. I get 12, 2 times 6 minus 4 equals 8. And then I get 26 minus 6 equals 20. So I just plug back into all three segments.